So this should be recording now. So continuing with our subjects now, if you should be seeing my screen now, and we are moving into after the biology and after the evolution, systematics and evolution of marine mammals, we are going now to the ecology. Okay, and in ecology, I also include conservation, right? So, and the first element of this, one important element to understand the ecology of marine mammals is their population dynamics. And so I have prepared this presentation, and this is based on one of the chapters from the textbook. And I've prepared this presentation on the population dynamics of marine mammals. So let's start. You may have had some specific course on population dynamics. You may have studied some elements of population dynamics in ecology courses, because this is a branch of ecology. But anyway, I just wanted to start by revising one basic concept, well, two if you want, basic concepts. And then most of the lecture, like most of the chapter in the book, is about techniques to obtain data to study the ecology and the population dynamics of marine mammals. And the concepts I want to review are in this slide, okay? And it goes back to very basic elements of population dynamics. The first one is all living populations have the potential to grow exponentially. Okay, so that's the first thing. And the reason for this is, maybe not so obviously, is that during their lifetime, animals have opportunity, animals or plants, so living beings have the opportunity to produce more than one descendant. Okay, and if they're having and if they're having sexual reproduction, a pair has the capacity to produce more than two descendants during their life stage. Normally, they produce more than two, and in some species, and even considering just animals, but some species have the capacity to produce thousands of descendants, right? I'm thinking about fish. But even if you go to land animals like rats or rabbits, they can produce during their lifetime dozens of descendants. But even if they produce just two, well, if they produce just two, if a couple produces just two descendants during their lifetime, then the population will stagnate. And if there's any problem, the population will crash. But if they produce more than two, the result is that the potential to grow exponentially, right? Exponential growth can be slow, can be fast, but the characteristic shape of exponential growth is what you see here in the red line. Okay, so as time goes by, more and more individuals are added to the population. Okay, now so that's one element. All populations have the potential to grow exponentially. The other element is that this is not possible indefinitely, right? So populations cannot grow exponentially forever. Okay. You may have heard, let me just open a parenthesis here. You may heard, if you have more interest on the wider implications of ecology or in political ecology, you may have heard the expression that to believe in exponential growth, infinite exponential growth on a finite world, you must be mad or you must be an economist. And the joke is that economists have use exponential growth as a solution for everything, and you see economic growth, exponential economic growth, presented all the time as a solution to all the humanity problems. And you see all our politicians, most of our politicians, worried about growth. The European Union wants growth, and this is so pervasive that even the United Nations, in their development objectives, sustainable development goals, have put one specific goal for economic growth. And they present the way out of poverty they present economic growth as a way of escaping poverty. So whoever defends this, and you see how this idea is pervasive everywhere, but only mad people or economists believe in it, or ignorant people. Anyway, so closing the parenthesis. Certainly in ecology, we know as a fact that populations, although they have the potential to grow exponentially, they cannot grow exponentially, right? You have limits. You have limits of space. You have limits of food. You have interactions with other species, right? So, of course, interactions with other species in terms of food, for instance, but also in terms of predation and parasites. So what happens is populations we rarely see exponential growth in nature. What you tend to see in nature is some sort of balance, right? The populations, we have this perception that populations tend to have a stable number. And of course, then this means that their potential to grow exponentially is controlled, is regulated. And so most of the work, the actual work in ecology, is studying what are these forces that keep population from growing exponentially, right? And so the second line that you have there is a very basic equation that was derived to try to model this tendency of species to not grow exponentially. And so this is a very basic equation, and you have the equation there on the screen. But basically what it does, it's based on a model where populations limit themselves, right? So when population starts to grow, there is less resources. The idea is that there is less resources, whatever those resources are. And so the birth rate decreases and the death rate increases. And so the population, by intra-specific competition, because the resources are not enough for everybody, the population will then slow its own growth through the balance of how many individuals are born and how many individuals are dying, until they reach an equilibrium. And this equilibrium is represented there by K. So there's in this model of logistic growth, there's a limit. Populations grow until they reach this limit, and that limit in the equation is represented by K. Okay. I forgot to mention that the growth potential is represented by R. So R is the growth potential of the species. K is the limit for populations that follow this logistic growth. So this is the basis. And now in ecology, you often find this concept of R species and K species, or to be more precise, R selected species and K selected species. And there are features of so this is a spectrum, right? So you species at one end of the spectrum, say the R end of the spectrum, tend to have short lives and to produce lots of descendants. Okay, so you have this is just for animals, but you have that. It's more obvious in animals really, So you have animals like clams that can produce, let's take that number, 500 million eggs per year, or fish that can produce weight 8,000 eggs per year. And they also tend to have short lives. So the species at the R end of the spectrum are normally small, and they tend to have short lives. Fish, many fish, I mean, not all. Rabbits, rats, mice, those kinds of animals. And then at the other end of the spectrum, you have case-selected species. And case-selected species are species that are very well balanced. So, oh, sorry, give me a moment. I didn't log in with Zoom, and now it's threatening to close the class. So I need to go here and do my login. So just need a second. So weird. Let's see. This should have worked, but it's still giving me 9 minutes. It's still giving me 9 minutes for this meeting, which is a bit stupid.
If you maybe you need to, for the recording, yeah, it will be cut. If you want, I can become a host because I have Zoom subscription, but I don't know.
Oh no, it's not necessary. I mean, yes.